So, before a massive piece of electrical hardware like a transformer can join the power grid, it has to go through this whole series of intense exams. And I'm not talking about a simple checkup. No, this is a full-on certification process to make absolutely sure that when it gets plugged in, it's going to perform perfectly and, not cause a total catastrophe. Okay, let's dive into how they do it.
We're talking about transformers, right? These things are the silent workhorses of our entire electrical world. I mean, a single one of these can power an entire neighborhood. But with that much power comes a huge responsibility and a really big engineering challenge. How do you prove it's both safe and efficient before it ever sees a live wire?
And that right there is the core of the problem. If you want to know how it'll perform under stress, you got to stress it out. But how on earth do you push a machine designed to handle megawatts of power to its absolute limit without needing a dedicated power plant just for the test and without risking a citywide blackout? Well, that's the puzzle we're going to solve today.
So here's the game plan. We're going to walk through the engineer's playbook, step by step. First, we'll see how a transformer gets its initial checkup. Then, we'll decode its fundamental characteristics. And after that, we'll put it through this incredibly clever stress test. Finally, we'll see how to make sure it can work with others before we put the whole story together. All right, our first stop is a pair of really fundamental diagnostic tests. The best way to think about this is like we're reading the transformer's genetic code. These are the open circuit and short circuit tests, or as you'll usually hear them, the OC and SC tests. They tell us pretty much everything we need to know about its basic efficiency and behavior. The easiest way to get your head around these two tests is with a car analogy. The open circuit test, that's like measuring your car's fuel consumption while it's just idling in the driveway. The short circuit test, on the other hand, is like finding out how it performs when you've got the pedal to the metal. Two totally different conditions, and both reveal absolutely crucial information.
Okay, first up, that idling test. Even when a transformer isn't actually delivering power to a load, it's still sipping a little bit of energy just to stay energized. This waste, which shows up as heat in its iron core, is called core loss. It's kind of like the baseline cost of keeping the lights on.
So how do you measure that idling loss? Well, in the open circuit test, we apply the normal rated voltage to the input side, but, and this is the key, we leave the output side completely disconnected. With no load attached, the tiny bit of power the transformer draws is exactly equal to those core losses. It's simple, but really effective. Now, for the pedal to the metal part. When the transformer is actually doing work, delivering current, a totally different kind of loss takes over, copper loss. This is just the heat that's generated by the current flowing through the resistance of the copper windings. The more work it does, the hotter it gets, and the higher the copper losses. To measure this without blowing anything up, we do the short circuit test. Here's where it gets clever. We intentionally create a short on the output, and then we apply just a tiny fraction of the rated voltage to the input, just enough to drive the full rated current through those windings. This brilliantly mimics the full load current condition without needing massive amounts of power, letting us measure the copper losses precisely. So here's the payoff. With the data from just those two tests, the idling test and the full throttle simulation, we can build this, the equivalent circuit. This is a complete electrical model, a DNA map, that lets engineers predict exactly how the transformer will behave under any condition. They can calculate its efficiency and voltage regulation without ever having to connect it to a real, full-size load. But wait, what about temperature? That DNA map tells us about efficiency, but it doesn't tell us how the transformer is going to hold up after running at full blast for, say, 8 hours straight. For that, we need a long-duration stress test, and that brings us to an incredibly clever solution, the sumpner's test. The problem, like we said at the start, is energy. Actually trying to run a huge transformer at full power just for a test is unbelievably wasteful. You'd be burning a massive amount of electricity and just turning it all into heat, all for the sake of a measurement. It's not just inefficient, it makes testing the really big transformers practically impossible. There has to be a better way.
And of course there is. It's called Sumpner's test, although you might also hear it called the back-to-back or regenerative test. And the concept is just pure engineering elegance. Instead of testing one transformer against some giant, power-hungry load, you make two identical transformers test each other.
Okay, here's the setup. You take the primary windings, the inputs, and you connect them in parallel to one power supply. Then you take the secondary windings, the outputs, and connect them in series, but you wire them to oppose each other.
This is the magic arrangement. One is trying to push voltage one way, and the other is pushing back with the exact same force.
And here is the absolute genius of this test. The first power supply provides the rated voltage, which takes care of the core or idling losses for both transformers. Then a second supply injects just a small voltage into that secondary loop, but it's enough to circulate the full load current through the windings of both machines, creating the full load copper losses. They are both running at full load conditions, getting hot, getting stressed, but the only power you're actually drawing from the wall is the tiny amount needed to cover their combined energy losses. It's brilliant! So our transformer has passed its physical. We know its characteristics, we know it can handle the heat, but out in the real world, on the grid, transformers rarely work alone. They're team players, so the final step is to make sure it can actually play well with others.
The best way to think about operating transformers in parallel is to picture two people carrying a heavy couch. For it to work, they have to be matched up, right? If one person is way taller than the other, they're not going to share the load properly. And most importantly, they absolutely must lift in the same direction. Because if one lifts up while the other pushes down, well, that's going to be a disaster. This brings us to a classic engineering exam question, a Viva question, that every student has to know. What are the absolute non-negotiable conditions that you must satisfy before you can connect two transformers in parallel? There are 4 critical rules. They've got to have the same voltage ratio, so they share the load correctly. They should have the same percentage impedance, which is basically their internal resistance, so they share the load in proportion to their size. For 3-phase transformers, they need the same phase sequence, making sure their power cycles are in sync. But the most critical one of all is having the same polarity. So when you're connecting them, as you see in this diagram, there is one final, absolutely critical safety check. An engineer will place a voltmeter right across the terminals of the final switch before they even think about closing it. That one little meter reading, that's the moment of truth. If that voltmeter reads 0, it means the transformers are perfectly in sync. They're pushing in the same direction. You're golden. It's safe to close the switch. But if it reads anything other than 0, especially if it reads double the rated voltage, that means the polarities are reversed. They are fighting each other. Closing that switch would create a massive explosive short circuit. It's the one check you can't get wrong. All right, let's pull all this together and recap the whole journey. From a standalone unit in the lab to a certified piece of hardware that's ready for the national grid. We started with the OC and SE tests to get the transformer's DNA. That was our car efficiency check. Then we used the super clever Sumpner's test, our 2 wrestlers, to check full load performance and temperature rise without wasting a ton of energy. And finally, we verified the conditions for parallel operation, making sure our couch carriers can work together safely. In the end, all these lab procedures, they produce the critical data that generates performance curves for efficiency and regulation, the exact kinds of graphs engineers rely on. This is how they can guarantee with mathematical certainty that a transformer will be safe, efficient, and reliable for decades to come. It's a whole hidden world of testing that keeps our modern lives powered. Which kind of makes you wonder, right? What other hidden tests keep our world running?